OpenCL has not only a personalized computational model, but it also presents a different way to manage the communication among hosts and devices and a different organization and accessibility of the available memories. So let's now move to better understand the OpenCL memory model. In the OpenCL memory paradigm, there are mainly three layers of memory: a global memory, which is shared among host and device; a local memory, which is accessible by all the work items inside the compute unit; and a private memory, which is accessible only to the processing element or single work item. In case of an OpenCL device powered by an FPGA, we can physically map each of these memories as follows. The global memory is the data RAM or DRAM on the device, which is accessible by the host via PCI Express. The local memory are the block RAM on the FPGA, and the private memory are the registers on the FPGA. It's important to notice that OpenCL memory model does not allow the host to directly send data to the device. Whenever we want to move data from the host device to our FPGA, in fact, we need to first move it to the global memory, and then our FPGA will be able to access it. The same story applies when we want to read the results of the computation. The FPGA is not allowed to send data directly via PCI Express. It needs to write the results to global memory, and the host will be able to read them. This diagram reflects what it has been described so far in terms of memory model. Furthermore, we can notice that there is a memory that we did not previously describe, the constant memory. This is a specific area of the global memory that is hosting read-only variables for the compute kernel. From the picture, it is clear that the host memory, that we identify as RAM of our device, is accessible by the host only, while the global and constant memories are accessible both from the device and the host. Then we have the memories that are accessible from within the device only. These memories are the local one, that is inside each compute unit and accessible by all the processing elements inside the unit, and the private memory. This last memory is personal of each processing element, and only the specific processing element can access it. Let's now try to summarize both OpenCL computational and memory model with a simple picture. We know that we can have a host communicating with multiple devices. But for this example, let us assume that we have a single device and that this device is an FPGA board. Our host has its specific memory that is necessary for executing the host program. Then, the host is responsible for allocating the memory buffers on the global memory so that the input data to our kernel can be provided. Once this kernel has been created and populated with data from the host, the computation on our kernel can then start. At this point, the kernel will organize the input data in the specific local memories of each compute unit, so that it can be accessed by all the elements inside the compute unit or workgroup. To allow a faster program execution, it is then possible to further move data using the logic of the FPGA and store them into private memory of the basic element provided by OpenCL for the computation, the processing element or work item. Obviously, when designing the hardware architecture, the designer will have to take under consideration that the more private memory is used, the more logic will be occupied on the FPGA. Besides, the closer the memory is to the work item, the faster and smaller it is. In fact, the global memory is the space usually qualified to keep the greatest amount of data, gigabytes of data, while private memory is used to store the elements, kilobytes, that are needed within the clock cycle. To increase the level of parallelism on the FPGA device, the designer can increase the number of compute units that are instantiated on our device. In this regard, it is important to understand that when running on an FPGA, the processing elements do not work in parallel, but as a pipeline. This is one of the main differences between the OpenCL kernel running on FPGA with respect to the same kernel running on the other architecture, like GPUs. While the computation takes place on the device, the host will be able to perform other operations, such as instantiating other kernels or managing different devices. Once the computation on our device will be over, the kernel will expose on the global memory, in particular on a particular buffer created by the host, the results of the computation that can be read from the host using the PCI Express.